Okay, great. Right. Good morning, everyone. Let's see here. I flattered. I didn't think all these many people would show. I was told it would be less than this, but I always say the more the merrier. I just want to get an idea just to kind of tailor the lectures. Like, who's in the classroom here? Like, how many people are undergrads? How many people are grads? How many people are Sloan? So, grads, raise your hand. Grad students? Okay, undergrads? Okay, and then MBA or Sloan students? Wow, okay, great. Okay, well, you've probably read, I'm guessing you read the course syllabus and you know a little bit about what this class is about. We're going to talk about what's kind of been the driving passion in my life for the past 30 years on lightweighting and how to make things strong and stiff and light and what that does for you and the tools that have been developed to do that. Here's a course agenda. Okay, so first thing we're going to talk about today is we're going to talk about what is lightweighting, why is it important, what does it buy you. We're going to go over some notable examples of lightweight design. So there's the aerospace industry, the car industry has been working on this for 100 years or something like that, and so there's lots of good examples out there, I think, of milestones in both cars and bicycles and airplanes, and we're going to talk a little bit about tennis rackets. Tomorrow, or next week, we're going to talk about design and materials. So you folks should feel very lucky because I think one of the world's expert on the topic of design and materials has actually recently become a professor here. You guys know Greg Olson yet? No? Okay, so Greg Olson was on my committee when I was a PhD student, and he was one of my favorite professors. He is an incredibly brilliant person, but he's really the guy who's, I think, done a lot to be the inventor of the topic of design of materials. So designing, not just saying what values can I get for strength or stiffness or whatever by looking at a book, but how can I actually design a material to give me the properties I need that will make my design or my structure better. The third lecture, we're gonna get a little bit more mathematical. We're going to talk about beam mechanics. We're going to talk about what I like to call the constitutive laws of weight savings. I'm not sure that's a rigorous definition of what they are, calling them constitutive, but I'm just going to call them that because it's an easy word to pick up. And then we're going to talk about car structures, primarily body structures, and how we can then apply what we've learned with these beam mechanics and laws and weights and materials, how we can apply that to make lighter automotive structures. The fourth lecture, we kind of changed things a little bit. We're going to talk first about numerical optimization. So numerical optimization, I think, is a very, theoretical, conceptual thing. Very, very math intensive, now very computer intensive, but numerical optimization and how you use this mathematical tool to make lighter structures. Talk a little bit about finite element analysis. Have you guys already had an FEA course? Who in this room's had an FEA course already? Okay, so not that many. So finite element analysis is a critical, ubiquitous tool used throughout industry. It's incredibly complicated from a mathematical perspective, and without modern computers, it would be totally useless for practical application in automotive or airplanes. But amazing tool. We'll talk about sort of the math behind that, just so you get an understanding of where the alligators are buried. What are some of the assumptions or approximations used in finite element analysis, because that can affect how you interpret the results. Lecture 5, we're going to start talking about some of the structural optimization tools that have recently, I'd say within the last maybe 10 years or so, become very useful. These are structural optimization tools that use finite element analysis and numerical optimization together to give you an idea of how to better design a structure. Incredibly useful tool, and I have a long lecture there to show you exactly how kind of everything goes together. Okay, the final lecture, lecture 6, talk a little bit about some of the other factors that go into structural optimization. Fatigue, joint design, some things like this, and then we're going to go through, I'd say, the history of car body design, starting maybe like in the 50s, or actually earlier than that, actually in the 50s, and then go through modern to show like how these things have changed with both understanding of materials and fabrication processing methods. Then we're also going to talk about racing bicycles. I understand from talking to Professor Eager, this is something that a lot of students like, so we're going to talk about racing bicycles. It's a topic that's important to me. So, and bicycles have actually very closely mirrored airplanes and cars and how they're optimized and made lighter and stiffer and stronger, more fatigue resistant. Okay, any questions about the agenda? Does this make sense to you guys? If you want to add, if there's anything you want to see here that's not there already, let me know. Okay. Okay. So here's the deal, guys. When I was an undergraduate, I used to annoy the hell out of everybody because I was always asking questions. I used to get notes on my desk saying, "Stop asking so many questions." It's because I've learned, for me at least, that being an active learner is much more productive than being a passive learner. So if you have any questions you want to ask me, anything you want to blurt out and stop, just do it, okay? Any questions you have, just stop me right where I am. We can talk about anything, okay? And I've recently given a lecture that's very similar to this to one of my companies, one of my clients, and that's how it worked. They asked, there was lots of questions, and I think everybody learned a lot more as a result of asking questions. So let's see. I should also mention again, my name is Don Baskin. I've got a PhD in material science and engineering, and I have a consulting company that I own called Spectrum Materials Engineering, and I have a variety of clients both in materials and consumer and automotive, a variety of different companies making different things. Anyway, okay. Any questions on this? Okay, again, if you have any questions, just blurt it out. It's okay. I don't get offended. Okay, lecture 1. Here we go. Okay, how many guys have heard about the topic of light weighting? Have you thought about this very much? Have you seen this other places? A couple of Sloan guys raise their hands. Okay, so what is light weighting? What does this topic really mean? I mean, I guess the name light weighting is pretty self-explanatory, right? I mean, you make something lighter, okay? But I think it's a concept I think that's very much talked about in automotive. It's very much talked about in bicycles. It's very much talked about in the aerospace industry, trains. Trains are close to airplanes almost. It's sort of the idea of you take something, a current design that exists, and you find a way to make it lighter. Okay, and this can happen through a variety of methods. Okay, the best way to get good light weighting is to start from a clean sheet. Rarely do you have the opportunity to do that, and sometimes you gotta do what's called material substitution, take an existing design and maybe back substitute with a material. But when you have the ability to start from a clean sheet, that's where you really can get what's called greatest structural efficiencies. Okay, that's really the route to start from, if possible, although that's not always possible. So you want to make a design typically that's lighter. I mentioned that. In most design engineering teams, when you're designing a car or a bicycle or a train or a shock absorber or whatever, there's always design objectives. It's got to be so stiff. It's got to be so strong. It's got to function within these parameters. It has to last 150,000 miles or whatever that number might be. Okay, so you have to lightweight typically, but you don't have the luxury of saying, forget about that other stuff. Forget about these design objectives. We don't care if it falls apart in 50,000 miles, even if we told the customer it's going to last 150. So you have to meet these design requirements. So structural optimization or light weighting, I'll use those two, they're kind of the same thing. The concept of light weighting, making lighter structures lighter, has probably been around forever since they had chariots drawn by horses. But I think the first kind of discussion that I ever read about it was from the late 1700s. The see if I can pronounce this right. The Montgolfier brothers. I took French, but I still can't pronounce it. They were into balloons, and they were the first. I think this is the first time in the late 1700s, since 1783, that guys actually put themselves in a balloon and went up in the atmosphere. And they got to, 10, 15,000 feet, whatever it is, and found out how cold they were. They think it was somewhere near Paris. And they had a lot of interesting drawings. But you can kind of see, that's where I think the light bulb went on. And people said, if the gondola, the thing that's holding me to this balloon, is lighter, then I'm going to go up further. And they always wanted to go up further to see more, okay? But this is like a classic Archimedes problem, right? I mean, you have the balloon, it's displacing some amount of air. As long as that balloon volume is lighter than the air volume, it will continue to go up. So you've got one force vector up, which is related to Archimedes' force, and one vector down, which is the weight of whatever's in the gondola. Okay? The lower that down force is, the further up you're going to go, because you're going to get to a certain point as you go up in the atmosphere that the air becomes lighter and lighter, right? And then you're getting diminishing returns there. The balloon has to be lighter and lighter and lighter in order to keep going up. So at some point, at some altitude, as the Earth thins, you reach some equilibrium. Okay, and so the lighter you can go on the gondola, the better off you are, right? The further up you can go. Since then, it's become really, I think, a topic with airplanes and racing cars, bicycles, to lighten, to always find lighter solutions that meet strength and stiffness, etc. So the industry, starting probably in the mid, I don't know, 1900s, kind of started developing a lot of interesting tools. NASA, as well as the NACA, the predecessor to NASA, I think they were really very instrumental in developing some of these tools, like finite element analysis, like structural optimization, topology optimization, topometry optimization. These are tools and methodologies that have become very important in lightweighting, that have really pushed the needle, enabled lighter, stiffer, stronger designs. We're going to talk a little bit later, I think, in one of our later lectures here about these tools, and we're going to kind of go through the history. And some of the initial tools are kind of parochial, but as you go on, you'll see they get much more sophisticated. Biomimicry is also a big topic. You know, how do you copy nature in order to make lightweight structures? So birds are really nature's aerospace engineers, right? I mean, they got to go up in the air, they got to fly, they got to catch other birds or catch animals on the ground that they want to eat, whatever it is. And they actually have hollow bones with webs inside of them. So bird bones. I mean, it's a really fascinating example of how that works. That nature evolved these hollow structures to make birds more lightweight so they could fly higher and go faster. Topology optimization is a tool that we're going to focus on. We're going to talk about a lot. This is a tool for optimizing load paths. The two examples you see here are topology optimization. This is a suspension component for a car. This is something I worked on when I was at Chrysler. This is a tool we used. We used topology optimization to reduce the weight of an SUV structure. And then we'll talk about a bunch of other tools. Okay, so you guys understand what lightweighting is? Does that all make sense? Any comments, questions? Today's going to be a little fuzzy, guys. It's not going to be real mathematical. It's not meant to be. It's just to be sort of, this is conceptually where we are and what this tool, what we're talking about and where it's been and so forth. And so show some examples, okay? Okay, so why is lightweighting important? Okay, so reason one I'll start with is reduced use of gasoline or diesel fuel or kerosene on jet planes. The Department of Energy has published the numbers that they say for every 10% weight reduction of a car, you can save 6 to 8% in fuel. Okay, so that's a nice amount of money you can save. That's, a couple beers a month probably at least, especially given what beers cost in Cambridge. Okay, weight reduction as far as cars are concerned or buses is really much more important in city environments where you're stopping and starting a lot, where you're stopping and then accelerating, stopping and accelerating. Once you get on the highway in a car, the equations become very different, and drag, aerodynamic drag, becomes the dominant force that sucks up your gas. So you probably know that the drag force is a function of the frontal area of the vehicle and the velocity squared. So you can very quickly see that because it's a velocity squared, as you start going faster, like you do on the highway versus in the city environment, you start burning a lot more gas. It makes sense. And it becomes so overwhelming at about 50, 55 miles an hour that weight doesn't become much of an issue. Okay, reduced CO2 or greenhouse gases. Okay, I think this is obviously a hot topic right now. There's a lot of discussion with rising oceans and what that does to the environment and CO2 in the atmosphere. I don't want to get too political here, but I think there's a lot of data out there. Some of it probably derived here at MIT that talks about CO2 and how bad it is for the atmosphere. But this is a number that actually astounds me. It said for every gallon of gasoline you burn in your car, you produce 9 kilograms, which is about 20 pounds of CO2. Okay, so a gallon of gas weighs between like 6 and 7 pounds, which is, what is that, like, someone convert that to kilos. That's like 4.5 kilos, I think. I think it's like 4. It's like mid fours or something like that kilos, or 3 to 4 kilos. Okay, so, but you look at the gallon of gas weighs. Sorry to mix units here. The gallon of gas weighs 6 to 7 pounds, produces 20 pounds of CO2. How does that happen, right? That doesn't seem to be conservation of mass there. But you have to take into account all the air that goes into that reaction to burn the fuel. So that air, there's so much of that air, so much oxygen that goes in there, you get so much more CO2. So that's a really scary thought when you think about CO2 emissions and what it does to the environment. in this country, in 2018, we burned about 150 billion gallons of fuel. That's diesel and gasoline. Okay, that's about 1.3 trillion kilograms of CO2 in the atmosphere. That's one country. Pretty scary stuff. And then if you think about if you could reduce your vehicle weight by 10%, that would translate into about 108 billion kilograms less of CO2 in the atmosphere. So that's pretty shocking to me. So much CO2, and reducing 100 billion seems like 108 billion kilograms of CO2 seems to be pretty compelling reason to reduce weight. Any questions on this one, guys? No?
Actually, yeah.
Sure, go for it.
Go back.
Yep.
So using 150 billion gallons of gasoline, but is most of that used in city driving? Because I've driven across the country 3 times in the last 2 years.
Yeah.
As have a lot of my friends. Most of the gallons of gas are probably used in the trucking industry.
It's a good point. Good catch.
Will 10% reduction of the weight actually be a 10% reduction?
So back of the envelope calculation, but she's absolutely right. So just
for the people watching, can you repeat it?
yeah, I'm going to do that right now. Okay, so what's your name?
Paige.
Paige. The point that Paige made, she caught an error that I made. Thank you. Okay, so it's a really good point. The point is that if this number that I have here, this assumes that all that mileage was city driving, which certainly isn't true. So the number's probably actually a little bit less than that, or maybe, I don't know, some percentage less. We can figure that out, what that is. I'm sure there's a place where we can look up online what the percentage of city driving is to highway driving. But the number's probably less than that. Regardless, suppose it was 50 billion kilograms. Would you still want to reduce that? I would. So, but it's a good point. It's a good point. Thank you. Okay, money. Saves money. So gallon of water or bottle of water weighs about a pound. 2.2 kilograms. Did I get that right? I'm sorry. Bottle of water weighs about a pound. 2.2 kilograms. The amount of money it takes to send that up to the International Space Station, the ISS, is somewhere between $10,000 and $25,000 to get that one bottle of water up there. It's pretty crazy. Believe it or not, the astronauts who live on the International Space Station, they don't actually ship them water. They recycle everything. So think about what they're drinking. I'll leave it there. You guys can probably film the details. It takes about $1 to $10 to get that same bottle of water up into an airplane up in the sky, 30,000 feet, and fly 1,000 miles. And then for a car, it's actually pretty cheap. It's about 0.1 because you're not going anywhere. So what this means is that engineers who design airplanes, engineers who design spacecraft like Blue Origin or SpaceX or NASA, they're far more willing to pay for weight savings because there's a business case to be had there, right? They can get their money back because they're going to spend less in fuel getting that spaceship or that airplane up in the air. Okay, increased payload. So the trucking industry. So the trucking industry drives about 1.5 billion tons of cargo a year. That was in 2018 in the U.S. Okay, that's a lot of cargo. And for every pound that they can take off the vehicle, the chassis or the wheels or whatever, that's one more pound that they can put in the payload. So they can earn money on that versus lose money on that. Consequently, the trucking industry is also very willing to spend money on light weighting. They're much happier to do it than people and companies that are making cars like a Chrysler or General Motors or Ford or an Audi, whatever. Okay, any questions on this slide?
Just a comment. I worked at Boeing before coming to the LGO program here, and I was actually in the weight and mass properties group. So
okay.
A lot of my job was working on the new 777X airplane and trying to do basically both of these points where early in the design program, if you were going to save a little bit of money, you could add weight to the airplane, but like right now, if you want to put a new design change in that's going to save money, it has to save multiple thousands of dollars per airplane to add a single pound. So forces that point.
This number, $1 to $10, I have access to the internet. That's where I get those numbers from, and I found anywhere between $1 and $10, right?
Yeah.
To get a water bottle into 30,000 feet, right? But what wasn't clear to me was whether that was, and maybe you can answer this, was whether that's how much you'll spend to get it 1,000 miles once it's in the air, or does that include takeoff as well?
I think probably talking about different things. So
Okay.
for me, basically, you have a cost, right, to design the airplane. And so any changes you make to the airplane are going to add cost or subtract cost, right? It's also going to affect weight. So early on, if you're going to make a change that saves a little bit of money, you can add weight. But later, when you're still trying to meet all those design requirements and customer commitments, if you're going to add 1 pound or 10 pounds, you have to save a whole boatload of money, closer to the multiple thousands per airplane, because that might displace a passenger.
Right, exactly, and that's the same thing about a pound in is a pound off is a pound in. If you can take weight off the airplane, you can put more passengers, and you can get those fares for those seats that you've sold. So there's a whole area in this. They call it industrial optimization. Is that the word for it? There's departments that figure these things out. Operational optimization. Anyway, there's research departments. I'm sure there's one here at MIT that does these kind of calculations. Okay. Another point I should mention here that I wanted to mention before but I didn't was that there's a downward compounding effect with weight savings. So if you take a pound off the body structure or 20 pounds off the body structure of a car or an airplane, a fuselage structure, that means that, for example, in a car, if the body structure, that means maybe you can make the engine lighter because there's less to accelerate. You make the engine lighter, then there's the possibility of making the suspension components lighter. And then there's a possibility of putting in a smaller gas tank. And then there's a possibility of putting in a less heavy wheel or a smaller wheel. So there's an effect here where you get weight savings that compounds. So weight reduction begets more weight reduction. It's actually very, very acute. Most people don't realize how much you can really reduce once you start reducing other things with it. Okay, another thing about light weighting. So in this country, we have regulated gas mileage. The car manufacturers are regulated by the National Highway Traffic Safety Association to have an average fuel mileage for the fleet. So the Department of Transportation says we want cars to get better gas mileage for national security reasons, for environmental reasons, probably national security reasons more than anything, so they don't have to buy oil from other places. And, they mandate NHTSA, National Traffic Safety Association, Highway Traffic Safety Association, to enforce this. And then there's what's called the corporate average fuel economy. So the corporate average fuel economy is an average of the fleet of a given manufacturer. They have to meet a certain target for fuel mileage, and it's not the same for every car. The government has a bit of a heart here. They break it up into different categories. So depending on the sort of the footprint of the vehicle, so the length times the width or the wheelbase times the track, okay, and they have different size classes, and then each of those size classes has their own independent fuel mileage requirements. And then there's what's called a harmonic average, which I won't get into. It's kind of complicated, but they do what's called a harmonic average, and that comes out to what the corporate average fuel economy is. So right now, car manufacturers are required in 2020 are going to be required to have a fleet average of 35 miles per gallon. Got a question, Paige? You look deeply distraught. Huh?
Well, $5.50 per car sold isn't a whole lot.
When you're selling millions of cars, it is. Right. So the penalty is brutal. If you for every 0.1 miles per gallon, you're below that 35 miles per gallon for your fleet, you have to pay $5.50 for each car. And if you're selling millions of cars, it's a lot of money. In fact, I think I read since 2008, the U.S. auto industry has paid something like $390 million to the government because of fines from CAFE.
Didn't Volkswagen save on the order of $1 billion by falsifying their fleet average? That's a fact.
Oh, it's a fact. That's right. I mean, but the cars were running a different fuel usage algorithm. You know, when they were being tested than when they were being driven. So they sort of game the system.
Does this take into account ethanol in the gas?
It's a good question. I don't know the answer to that. I can find out. A lot of the research that's done for CAFE is actually done on Broadway here at the Volpe Center. You guys know that place? It's on the other side of Broadway. Yeah. So they do a lot of the research for this.
Just another question. Is the fleet average weighted by the cars sold or just by what they offer?
Sold.
Oh,
Sold, yeah.
Okay.
Right. So an interesting point here though is that a company like Ferrari, for example, they don't sell. Ferrari sells 10,000 cars in a year. That's an amazing year for them. That's a record year for them. They sell a lot less. They typically sell 8,000 or 9,000 cars a year. And you can say, okay, they got a bunch of cars with V12 engines or high-performance V8s. Maybe the cars are getting 20 miles a gallon in the best-case scenario downhill in a hurricane. Okay, so what does a company like Ferrari do? Because there's no way they're going to be 35 miles a gallon for their fleet. And what they do is they just figure they're going to pay for it. They just plan on paying for it, and they pass the costs on to their customers. Now, it used to be before, I think Ferrari went public in 2012 or something. Before they were part of the Fiat group, so they could sort of average themselves in with Fiat, who sold a lot of small cars, especially in Europe. Okay, but when they went separate, when they got spun off into their own company, they just figured they pay for it. Okay, any questions on that one? Nope. Okay. So a lot of people will tell you that cars that are lighter handle better, brake better, have smoother rides. This is true. This is true. I've driven. I used to work in the automotive industry, so I've driven probably more vehicles than the average person, and I can tell you that there's a certain feeling that you get with a lightweight car, a certain ease and cooperativeness that you don't get with a heavy car. I don't really know why though. If you guys are smart, you've taken statics and you understand that the friction force of a wheel, for example, under braking or turning, is just related to the normal force times some mu, some friction coefficient, right? So if the car is heavier, the friction's higher too. The braking should all be the same, and the cornering should all be the same. There shouldn't be a difference. But the fact is that I've been to a lot of car races in my life. I've been to a lot of club level car races. I've done some racing myself, and I've seen how cars that are lighter with equal to power to weight ratios as heavier cars are still faster. And quite honestly, I don't really understand why. I don't think a lot of people do. I think it's kind of taken for granted that lighter means faster, but it doesn't necessarily. I mean, the math doesn't seem to work out there. And I think what's not understood here and why it actually does, you actually do it in faster, is because I think there's nonlinearities in the in rubber, in tire rubber, in bushings and suspensions, in oil and shock absorbers. There's some kind of weird nonlinear effect there that's happening where somehow these things perform better when the vehicle's lower or lighter. Having worked in the automotive industry for a decade and a half, I've had many conversations with friends of mine on this topic, and many of those friends were vehicle dynamicists about this topic, and we've had long discussions over dinner for hours and hours about this topic. And the best answer we can come up with is there's some nonlinearity. Something's nonlinear in the way the tires, the soft components are behaving: tires, bushings, oil, and shock absorbers, etc. Okay, so these are the 6 reasons I have for weight reduction. I think they're pretty compelling. You guys have any questions about those? Okay. Some weight savings is worth more than others. So BMW, for example, is well known to break up the weight savings on their vehicles by position in the vehicle. Lower center of gravity is something that can always give you better braking, shorter stopping distances. That's not to say the vehicle's lighter, just to say the center of gravity is lower. Better in corner, you can get more work out of tires under braking and cornering when you have less weight up high. So BMW is famous for willing to spend more money to reduce weight high up in the vehicle. And then BMW is also fanatical about 50-50 weight distribution. It's always in their corporate brochures. And because of that, they'll actually spend more money to reduce weight in the front of the vehicle than the back of the vehicle. And then finally, there's what's called unsprung and rotating weight. So a wheel, a brake disc, these are items that move up and down in the vehicle when you hit a bump or go around a corner, okay? And they're also turning, okay? And if you've ever ridden a bicycle with heavy wheels, you know that it takes more energy to pedal a bike up to speed that has heavy wheels than light wheels. They'll typically spend more money also to reduce weight from brake discs, okay? Now, let me put an important point here. The wheels on the vehicle, although would have a huge effect on fuel and handling and braking, they're dictated by styling. So the design group, the styling group, the product design office has first dibs to say, this is what this thing's going to look like, and I don't care what it weighs. Okay, they have that luxury. I understand why. Styling design sells cars. It's a fact. I've seen it firsthand happen. So they have to do that. But there are car manufacturers that will spend money to reduce weight in brake discs, for example. Audi notably does that. Mercedes does that. Ferraris and Porsches and Lamborghinis have these. Some of them have these ceramic brake rotors, which are a lot lighter. And there's an example where they're spending crazy money. Now it's a lot of money to spend, and a lot of it's quite honestly is vanity because most people aren't really going to use the capability of their ceramic brakes. But putting that aside, there is weight reduction there that's important. So anyway, just to put the order here. So the first thing the most important, the biggest bang for the buck weight savings is in suspension and rotating components, unsprung and rotating, then high up in the vehicle, then in the front of the vehicle, then in the back of the vehicle. This is sort of the hierarchy of where car companies will typically spend money on weight savings. So BMW, the European manufacturers tend to be much more interested in this. The domestic manufacturers tend to not worry about it so much. Okay, so probably should have gotten this before, but I wanted to put this now after a little bit of discussion. So you're probably wondering why listen to me? Who am I to be telling you about weight savings? Just some guy who showed up at MIT at 9 o'clock on a Wednesday morning. So I'll just tell you this. I spent a decade and a half working in the international automotive industry. I spent like a little over 2 years working at Mercedes in Germany. The first part of that, I was working in the materials research lab in Ulm, Germany. That's kind of halfway between Stuttgart and Munich. Anyone here has been to Germany, they know what it looks like there. In that position, I did research on brake rotor materials, ceramic brakes, intermetallic matrix composite brakes, brake rotors. Do you guys have any idea how many of you are car fanatics who know what a brake rotor is? Okay, a good chunk of you. I can show you pictures later if you're interested. But it's interesting. The ceramic brake rotors that you see on Ferraris and Porsches and Lamborghinis today were actually developed by Mercedes. They were developed in the department I worked in. Mercedes developed that technology. The technology had certainly been around before in racing cars, but the problem with racing cars is they don't have to stop when it's freezing outside, but street cars do. So the ceramics or the carbon-carbon composites that are on Formula One cars, they don't stop at low temperature, so they're not really good for production cars. That was the goal was to develop something that was more friendly at low temperatures, and the weight savings is quite substantial. It's about a third the weight of a cast iron disc. I also spent some good time working at the Mercedes Technology Center in Sindelfingen. Sindelfingen is a suburb of Stuttgart, just south of Stuttgart. This is where Mercedes has their main engineering center and main factories are there. In that role, I worked in the polymer matrix composites laboratory. We were working on using carbon fiber and fiberglass to lighten body structures. We worked on some interesting work with some material called Twintex, which is a commingled fiber of, we can get into this later, but commingled fiber of, commingled composite where you mingle carbon fibers with a polyolefin so that you can cook these things and then make a panel out of it. I can tell you more about this later, about what's called sheet molding compound. We also worked on some precursors to what's called topology optimization. We call them evolutionary engineering, where we were trying to use biomimicry to show or to mimic what happens with a tree. Okay, trees get thicker areas depending on how they're loaded. They sort of build up thicknesses in like the junction between branches and trunks and things like that. So we were trying to mimic that in the body structure in a car. Like how could we use that same technique to make a lighter car body? After working at Mercedes, I went back to Chrysler. At Chrysler, I was a real nuts and bolts engineer. I released 7 vehicles in the high volume production. I worked on the Chrysler 300C, the Charger, the Magnum, the Avenger, the police car versions of the Charger and the Magnum. I launched seven vehicles in high volume production. I spent months and months and months and months, months and months and months walking around car factories, launching vehicles, developed heel spurs, cut my hands, almost got run over, almost got killed once, got all kinds of burns around my neck from sparks in the body shop. Not exactly PhD work, but I'm glad I did it because it was a real experience to see how real cars go together and how real lightweighting can be implemented in a process that's production feasible.
So one thing I've actually always wondered about Chrysler stable cars, they're still quite heavy, especially
They are.
compared to some of their competitors.
They are.
What's the big hang-up with getting the 300 and the Charger? They're built on the same platform, right?
Yeah.
Why is that platform so gosh darn heavy?
Well, not only are they built on the same platform, but they're the same platform as the Mercedes E-Class too.
Right.
Okay, and the Mercedes E-Class is some couple hundred pounds lighter. So, I don't want to be disparaging of Chrysler. I mean, they have a customer. Their customer has certain priorities. It's a different customer than the Mercedes customer has different priorities, right? So, Mercedes, also being a European company, is under much greater consumer pressure to produce a vehicle that gets better gas mileage, because the price of fuel is incredibly high. It's like, whatever, $8 a gallon or something in Europe, $9 a gallon when I lived there. So because of that, they're much more focused on lightweighting. They'll use a lot of aluminum. The whole rear suspension on the E-Class is aluminum. It's all steel and cast iron on the 300. You start adding these things up, and it's hundreds of pounds. So they have to sell a car at a certain price point, so a certain customer is going to want to buy it. Mercedes is very different. It's a customer that says, I want a lighter vehicle. I'm interested in getting better gas mileage because I got to spend $10 a gallon, so I'll spend more money, for a car that gets better gas mileage. And it's that pressure that sort of pushes Mercedes to make a lighter car than Chrysler would.
What was your time at Chrysler? What was their biggest priorities for lightweighting?
Stay out of jail. I'm serious. And this isn't really criticizing them, because they have, like I said, they've got very different pressures than a Mercedes has. The idea was to meet CAFE, and that's all they wanted to do was just meet CAFE. They've been fined several times for not meeting CAFE, but to meet CAFE.
It seems like some of the work that you've been doing is like two different types. So one is developing novel materials. The other type is optimizing designs.
Yep.
What would you say the spread is between those two, the spend at these companies?
Mercedes probably spends a lot more money on advanced materials. When I was there, we built engines that had ceramic valves and stuff like that. Really expensive, silicon nitride valves and things like this. Really expensive. I should mention that after the last thing I did at Chrysler before I left there, the last thing I did after releasing these 7 cars into volume production and getting heel spurs and burns and cuts and all kinds of stuff that I still have, the last thing I did was I was asked to head up a team developing a process for lightweighting using some of these finite element analysis-based tools like topology optimization, topometry optimization, topography optimization. And one of the reasons they picked me was because I had worked on some of these tools at Mercedes. And so we carried those over to Chrysler, and then I was in charge of a team of 9 guys, and we actually developed these tools to make a process to make lighter body structures at Chrysler. And they still use that process today. And the reason I know that is because I still keep in touch with friends there, and I know they're still using it. Should mention this is Nimrod. We had to name these things because we didn't know what to call them. This is a topology optimization result of the structural optimization work we did. So the tools that we used developed this design idea, the concept, load paths, where to put mass for a body structure. Topology optimization results, they're called. And we put those results into a 3D printer back then, and we made this. But the lessons that we learned from this, some of the load paths that we discovered using this methodology, this one exactly actually went into the Chrysler 200. So I don't know if you guys know what car that is. I probably should put a picture of it, but some of the load paths and things we learned, this was the first car I think to take advantage of this, was the Chrysler 200, the so-called D-segment vehicle. So later on, I think it's lecture 4, we'll go into a lot of detail about how this is generated and what exactly this is. Okay? And you guys are welcome to come up after class and take a look at it.
Can you give some examples of how lightweighting also results in additional benefits, utilization benefits, like you mentioned? I'm thinking of
Right.
ceramic bearings and wheels not only reduce weight, but they also reduce friction, which
Right.
saves gas mileage.
Right.
Can you give some examples of where lightweighting is not just lightweighting, but
The compounding effect. Anytime you reduce the weight of a body, you can then put a smaller engine in. You put a smaller engine in, you get thinner suspension components, smaller brakes. There was I don't mean to push you off. We can find the study together, but there was a study done by U.S. Car in 2006 or 2007 called mass compounding. I'm sure we can get a copy of it. It's probably in the library upstairs. But it did exactly this. They actually went through and very methodically went through and did the calculations about if you take 1 pound off the body, what does it mean for the whole vehicle? We can certainly talk about that.
Would go into the business decision.
Absolutely.
Aircraft or automobiles or bicycles, and who your customer is, it would probably it would inform the decision of whether to make it. It's not all about lightweighting, in other words.
There's definitely business cases we had, right? And this is what I talk about. The car industry talks in terms of how much money am I going to have to spend to take a pound out of this thing? That's always a topic. How many bucks is it going to take a pound out? And I'll show you this calculation, I think it's lecture 2 or 3, where you look at how much money does it take to put in carbon fiber? How much money does it take to put in steel, high strength steel? That's why high strength steel is such a great solution for cars, because it's freaking dirt cheap. A lot of cases it's cheaper than potting soil you buy at Home Depot. Okay? But the strength increase is so high, and the stiffness of steel is way significantly higher than aluminum, that you can actually come out ahead sometimes using steel over aluminum, especially when you start talking about fatigue. But we'll talk about that later.
So, my understanding, like producing aluminum has roughly 6 times the carbon emission, at least to produce it.
Right. I don't know if that's the number, but I know it's more.
Yeah, it's like, depending on the alloy and like what you're using it for, it's like roughly 2 tons per kilogram for steel and 11 or so for aluminum. Do they also take that into consideration, the production?
The car industry won't. The car industry will just say how much money I'm going to pay. How much money I'm going to pay for this coil of steel. Stop. They're not thinking about CO2 emissions from making that aluminum.
Okay, so you could potentially spend more on, like, you could potentially do worse by switching to aluminum than using steel.
Oh yeah. Aluminum bodies are definitely a premium, for sure. They're never cheaper than steel.
Oh, I know cost-wise they are. I've worked on aluminum and it's ridiculous. But like in terms of they're all focusing on mileage or fuel efficiency, but they're spending way more on production to make these bodies.
You're saying in terms of like welding in the factory and so forth? Yeah. It's more difficult to spot weld aluminum, for sure. And the maintenance of having 2 separate populations of welding guns, for sure. Okay, we're running out of time, so I'm going to keep going here. I just wanted to show you some examples of some spectacular structural optimization. The first one here is the chassis of the Lotus Elise. This is made out of aluminum extrusions that are actually glued together using structural epoxy. I'm going to show you a slide at the start of the next lecture that's going to surprise you about what that really did for them and why they did it. It's really interesting how much they were able to save by not welding, but rather using glue instead. The next one here, number 2, that is actually the rear end of the Porsche Carrera GT chassis. And this is very interesting because it's the first time that somebody began to make sort of almost a space frame, what's called a space frame with carbon fiber, rather than just a monocoque. We'll discuss what that is later. Number 3 here, what I wanted to show here was actually this brake rotor, which is carbon ceramic matrix composite, and then the caliper. The caliper was designed using this topology optimization tool I keep spouting alpha about, and that allows significant weight reduction. The number 4 there, that is the suspension system control arms off a Acura NSX from the 80s, and I think this is one of the earliest examples of a auto manufacturer using topology optimization to design the geometry of that control arm. The number 5, that's actually the pedal structure off the Lotus Elise, and they this is fascinating because this is a very, I think, efficient use of material of aluminum. So what they did is they start off with an extrusion with the structure here that you see, and then they slice that extrusion up like bread, just like a loaf of bread, and then they use it for 3 different pedals. So it's a very efficient way to do a brake pedal structure, and lighter than steel. My favorite car, the BMW i3. This car is absolutely fascinating. I realize most people hate this car because they think it's ugly. It is, and I like the looks. Most people don't, but I can see why. The i3 is the first mass volume carbon fiber car. Okay, they're making hundreds of thousands of these things. That's the first time that's ever happened. And not only is the technical achievement amazing with that vehicle, but also what's really interesting about this vehicle is the supply chain accomplishment. They just didn't call up, a carbon fiber manufacturer and said, "Hey, send me all this, send me all these millions of tons of carbon fiber." They actually set up the whole supply chain with a German company called SGL. They built power plants in Washington. They set up pyrolyzation lines close to the power source. They put together this incredible supply chain, which I wouldn't say made it affordable, but got it closer. And yeah.
I don't know if I missed it, but was number 3, is that like a Formula 1 car?
It is. That's a Formula 1 car suspension and brake caliper. When I was at Chrysler, I did a couple different studies on light weighting of body structures. And I remember I went to the guy who was head of body engineering in the materials engineering department at Chrysler, a guy named Rick. I won't tell his last name, protect the innocent. But he said, Don, you're crazy. There'll never be a carbon fiber car. Even if the material was free, it costs too much to process the material. It'll never happen. Here you go, Rick. Okay, skateboard trucks. 3D printing. 3D printing will give us incredible ability that we didn't have before to realize topology optimization results. This is these trucks, I think, are from a local company. Maybe it's an MIT spinoff called Desktop Metal. You guys know this company? They're in Burlington. Everyone's laughing. Okay, anyway. Interesting application of topology optimization to a skateboard truck. Tennis rackets. When I was a kid, tennis rackets were like made out of aluminum. Now they're all carbon fiber. I was in Dick's Sporting Goods the other morning, and I was amazed. You can buy a carbon fiber tennis racket for like $30. It's amazing. It's amazing. When carbon fiber tennis rackets came out, they were $5,000, $6,000, $7,000, $100, like $1,000. I mean, they were really expensive. Now they've come down. Number 9 is my favorite topic, probably bicycles. This is a giant carbon fiber bicycle frame. It's made in Taiwan. It is, in my mind, the bicycle frame is the most highly optimized, from a structural perspective, consumer product there is. Your car, even a BMW i3, even a Formula One car, is nowhere near as optimized as that frame and structure is. These guys use topology optimization, they use shape optimization, they use carbon fiber, they use slave labor, all kinds of stuff to, that was a joke, they don't use slave labor. They use market value labor, sorry, to make these things. And it's amazing what they're able to do, and it's amazing how little they actually cost. The estimates are the people are thinking that this structure is like $50 to make. And they sell it for like $2,000, $3,000. So there's a big profit there. But we'll talk about that more. Here's number 10. This is the Boeing 787. You probably know about this one. They use a technique called filament winding to make the fuselage. When you're making composite structures, the name of the game is as many fibers as you can get in as little volume as you can get. So as little plastic, the most fibers, because the fibers are stiff, the plastic isn't. I had a friend at Chrysler who used to work at Boeing, and he once showed me a cross-section of a spar that came from the 787. And I was shocked. There was so much carbon fiber in there, it actually felt like it was metallic. Steel bicycle frames. We'll talk about that a little bit later. This is a steel bicycle frame that was optimized. Rather than just using tubes and lugs, this one was actually stamped from 2 shells and then welded together using advanced high-strength steel, a dual-phase steel. Cement. You can do cement too. So you can use structural optimization, topology optimization to make lighter bridges. The body structure, or the fairing structure, I should say, on the Porsche 908, the fiberglass was so thin that you could see through it. The Lotus Elise has the same situation. If you guys know what a Lotus Elise is, if you look in the trunk in a Lotus Elise when it's in the right way with respect to the sun, you can see the sunshine coming through. That's how thin the fiberglass is in the clam of a Lotus Elise. Okay, we're running out of time here. Let me try to explain this real quick. I started racing bicycles in the mid '80s. When I was racing, the state of the art was a steel bicycle with chromoly tube set. Okay, an alloy steel. Those tube sets were heat treated. The tubes were very delicately silver brazed together so you wouldn't upset the heat treat on the steel. The best case scenario was with a fork and everything, you got a 2-kilogram frame. The whole bike was 20 pounds, 21 pounds, and that was, if you were an Olympian, if you had resources to everything, maybe you would get a 19-pound bike for spending tens of thousands of dollars. Today, the bikes that won the Tour de France this year or the year before, the frames are 1.1 kilograms, so incredibly light. And then the whole bikes are by regulation are 6.8 kilograms, so lighter than they can go lighter than this, but the regulations of the sanctioning body of the bike racing, they say you can't go below 6.8 kilograms. Sometimes these bikes are actually made lighter and ballasted. So there's nothing wrong with steel. And we'll see this later. Steel has incredible strength, incredible stiffness per density. There's nothing wrong with the material. In some cases, some of those numbers come out close to carbon fiber. Not quite, but close. So there's a materials difference here between these two bikes, but also there's a huge geometrical difference. And this is what you were saying. What's your name? Sagar. This is what Sagar was saying, that there's two components to this. It's not just material. It's not just putting in a material that's less dense or has a better strength to density ratio or better stiffness to density ratio. There's also geometry involved. You have to design these shapes to be structurally efficient. But here's the problem. The materials guys are bored by mechanical engineering typically, and this is my experience working in industry. Typically, the materials guys are not that interested in mechanical engineering. Typically, the mechanical engineers aren't that interested in material science. But from my experience working with how many mechanical engineers we have in here? Okay, maybe you guys are different, but my experience working with mechanical engineers in industry is that they don't like material science because it's fuzzy. There's too much probability in material science. If the temperature is this and the atmospheric pressure is that, and I put this much chrome in it, maybe I'm going to get this phase, but there's some chance I'm not going to get this phase. I might get this other phase. And from my experience working with many mechanical engineers, that drives them batty. They love, and I got a mechanical engineering undergraduate, so they love the certainty of thermodynamics. You know, if I put this much energy in, somehow I'm going to get that much energy out. Okay, so I've tried to some extent, try to bridge this gap between the two, since I have an undergraduate in mechanical engineering and a graduate in material science, and try to put these together to make some sense of how you can go about lightweighting different structures. But the important thing I want you to remember today, if you don't remember anything else, is that lightweighting, structural optimization, is a function of materials and geometry. That's my lecture for today.